So with no further ado, I'm going to actually come over here and then introduce our first speaker, who is Tom Newson. And you heard about the mighty Princeton GFDL yesterday. There is no more significant institution in the world in terms of climate modelling than GFDL. I'll make the same introduction to NCAR in a moment. But Tom, I'm delighted that you can kick us off. Tom's going to speak using the case study of tropical cyclones and hurricanes particularly, but to highlight where climate modelling is currently giving us a degree of certainty in understanding future climate, but also use that to highlight where we're still facing uncertainties as we move towards understanding extreme events and extreme weather, which will be a focus of us. So, Tom, delighted you could be here. Thank you.
Thank you, Rowan, for that kind introduction. And good morning, everyone. I am going to be talking about climate modeling, focusing on Atlantic hurricanes, and the question, what can climate models tell us about Atlantic hurricanes in a changing climate, as an example? Because if we step back for a minute and look at what climate models can tell us in general, we can first look at things like global mean temperature, where we see it's quite well known now that the Earth's climate is warming. Climate models are our attempt to understand the climate system and why it's changing. And climate models are strongly indicating that the climate is warming due to the increases of greenhouse gases, because, as you see in the top panel, when we force climate models with the historical greenhouse gas changes, we are able to reproduce the warming we've seen since the late 1800s. But in the lower panel, when we do not include greenhouse gas forcings, we're not able to reproduce this warming. So climate models are strongly, it's one of the several lines of evidence that humans are causing this warming that we're seeing to date in the climate record. Now, turning to the future, climate models are also very strongly pointing toward a warmer climate future for Earth. And these are projections from the last IPCC report from a number of climate models forced by different radiative forcing scenarios going through the 21st century, and they're unanimous in showing a substantial projected warming over that time. But I would regard this as the easy part of the problem, global mean temperature. But what about, what else do we get with this warmer climate state? And one could talk about sea level rise, heat waves, droughts, ocean acidification. These are all terribly important problems that we do need to face up to. But today I'm just going to focus on hurricanes and climate because hurricanes can cause so much damage when they occur, as we saw in the case of Katrina in 2005. So, but hurricanes now enter a realm of a more difficult question in terms of climate modeling. And so if we look at these IPCC climate models and ask, what do they say about conditions over the Atlantic Basin in a future warmer climate? One thing they say is the models indicate that there should be some increase in vertical wind shear over the tropical Atlantic in a warmer climate, which actually should act to reduce hurricane activity. So we have this situation where we have warmer sea surface temperatures projected for the tropical Atlantic, but at the same time increases in vertical wind shear in this blue swath. So what I'll talk about in the remainder of my talk is an attempt to understand how these two things interact. And generally what we're seeing in the models is that this increased vertical wind shear tends to reduce the overall number of storms, the overall tropical storms and hurricane counts in the Atlantic. But the ones that do survive and come here, say from the coast of Africa, the ones that do survive this more hostile environment and make it north of this region of increased shear, then enter this region of where we do not have the increase of shear, but we have the warmer sea surface temperatures, and then they can really take off. So we have this situation we're seeing in models of fewer storms, but the ones that make it through this hostile condition can become really intense. And I'll show some of the evidence for that we're seeing from models as we go along. Before we talk about models, let's talk about data a little bit. This is some work of Kerry Emanuel looking at an aggregate index of hurricane activity in the Atlantic and Atlantic tropical sea surface temperatures. So these two time series are very well correlated. So it turns out when you have warmer sea surface temperatures, you have a greater degree of Atlantic hurricane activity. Now this correlation is disturbing on the face of it when we think about warming of the tropical Atlantic. In fact, if you take that same correlation and just extrapolate it into the future based on the warming of the tropical Atlantic predicted by climate models, you get this projection that we see in the upper part here. And again, this is the projection would be for something like a 300% increase in Atlantic hurricane activity, where just about every season would be as bad as 2005. So that's about as, if the climate's really headed in that direction, we really need to know about it. But it's not so simple, because the correlation does not make for causation. So we have this lower panel, a different statistical correlation. This time it's between hurricane activity and sea surface temperature in the Atlantic relative to the rest of the tropics. And you see that in that case, the climate models are not predicting or projecting that the Atlantic is going to warm more than the rest of the tropics. So it's a relatively flat projection. Very little change projected in aggregate Atlantic hurricane activity. So we have two different statistical models giving us very different future projections of the Atlantic. So which one would we put more confidence in? Well, it's hard to say because we're just using a statistical model. So but what we are trying to do is use dynamical models where we actually solve the equations of motion and try to actually simulate these hurricanes explicitly to try to differentiate between these two very different futures. And just to point ahead, the dynamical models are really pointing more toward this lower projection, which I'll talk about as we go along, with an important exception that I'll talk about as well. So now this is an example of a dynamical model that we might use.
John, just to say, I think we're going to be reasonably pressed for time, aren't
Yep.
we?
Yep.
So just
Yep.
probably another 3 minutes or so.
Okay, so this is a dynamical model, and it's we simulate year by year the variability of Atlantic hurricanes very well in terms of the past variability. You see the hurricanes that are being simulated in this framework. Now, if we then look at the simulation of hurricanes in a future climate, we see on the left a reduction in overall numbers of hurricanes in the Atlantic with this model, but an increase out here at the high end. And these are getting up around, say, 90-mile-an-hour hurricanes. But look, this part of the distribution of wind speeds of hurricanes is the observed distribution, and we're not even simulating them with this model that I just showed. So what we have to do is actually take all of these individual storms and resimulate them in an even higher resolution model to try to simulate these much more intense events where we start to simulate these hurricanes that can have wind speeds now up to, say, the category 4 and 5 of up to, say, even 160 mile an hour or more. Those are the storms we really care about. So we're using this much higher resolution model, and that one starts to tell us a different story. It starts to tell us that the fractional, in terms of percentage changes, yes, we see a reduction in tropical storms and hurricane counts, but when you go to category 4 and 5 hurricanes, it flips over and we start to see this increase. That's why when I talked earlier about these storms that make it through that more hostile environment, then they can really take off, and that's what we're seeing. And here are the tracks. Now, the upper is the current climate simulation, and the bottom is a future climate simulation, just looking at category 4 and 5 hurricanes in the Atlantic. And you see the more spaghetti there in the bottom. That's the roughly doubling in the frequency of category 4 and 5 hurricanes. This is by late in the 21st century. So it's very much a mixed picture of decreases in this overall number of hurricanes, but the ones that can make it through that increased vertical wind shear then can really take off, and we have roughly a doubling of category 4 and 5s projected. So, okay, I've tried to really run quickly through a number of things. I went from things that we're highly confident about, which is humans are affecting climate, and the models are projecting a substantial future warming of the climate, including in the tropical Atlantic. And I didn't have time to talk about it, but models are also projecting sea level rise. There are important uncertainties in sea level rise, which is going to cause more damage from storms, even if the storms don't change at all. And it's a huge uncertainty that we have to, the climate community has to try to resolve in terms of how much sea level rise and when. Now, models are projecting little or even no change or even reduction in run-of-the-mill tropical storms and hurricanes in the Atlantic, at least on average. And there's some uncertainty in this. So taking these average conditions, we're projecting fewer of them. But despite that, the ones that survive can then grow to be very intense. So we have roughly in our models, roughly a doubling in the frequency of the category 4s and 5s by 2100. But again, see this arrow on the left, decreasing confidence as we go down the page. What I've been talking about with hurricanes and climate is a much more difficult topic at this stage to make confident statements about than global mean temperature. So I'm just presenting the state of the science as we have it now, and we're going to continue to be working on this problem. At the bottom, I also note that so far we cannot really claim a detectable human signal in Atlantic hurricane activity because there's just so much noise out there, and we're looking for a fairly complicated signal. So I'll stop at that point, and thank you very much for your attention.
My congratulations for keeping to time, Tom, and setting a fantastic example. Just to let everyone know, in terms of the questions, we're going to do questions at the end, and the World Bank will ask us that people will, if they can write questions down on a piece of paper and hand it to the gentleman in the orange, beautiful orange coloured next shirt. That will be fantastic. Then we'll do the questions at the end. Or if you prefer, you can Twitter them by your Blackberries and they'll come on the screen. But, right, Tom, thank you again for some great stuff. I'm now going to move to another mighty US institution, the National Centre of Atmospheric Research, and Dr. James Doan, who I'm delighted to say is the Willis Research Fellow at NCAR, and he's going to take us a little bit further down in the journey in climate modelling towards how we can begin to think about applying that to understanding of risk, from hazard to risk. James, over to you.
Thanks, Aaron. Yeah, I'm a Willis Research Fellow at the National Centre for Atmospheric Research. And I'm interested in ways we can apply numerical models, these weather and climate models, to assessing risk. Now, when the traditional way to assess risk is applying statistics to the historical record, and when this came in a couple of decades ago, it really revolutionized catastrophe modeling. And it seems we're on the dawn of a new era in terms of risk assessment through the use of numerical models. So just to start with the point that computing power has recently advanced to a sufficient level that these models can provide information across scales. And by that, I mean we can look at information on the smallest scales of hurricanes right up to the climatology of hurricanes. However, of course, the finer the detail, the shorter the period we can look at. So we can only look at in detail at a few hurricanes, and we can only look at the climatology of the macro structures of hurricanes. So just a slide of motivation. Well, over the past 60 years, 80% of worldwide insured losses were weather-related, and that's dominated by tropical cyclones. And these cyclones, they don't come around periodically. They're subject to high volatility, and there's great uncertainty in the probability of a given event. So this more precise risk information that we may get from numerical models will allow a reduction in sharing of risk, and also for the industry a competitive edge. For example, new products, if climate change may open up markets in, say, South America, tropical cyclone risk. So I'm just going to go through a few ways in which weather and climate models can be combined for risk assessment. The first one being their ability to provide a base data set to generate new hazard event sets. This is some work we did at NCAR where we combined our weather and climate models to project tropical cyclones out into the future. These are cyclone tracks in the North Atlantic, on the left for the 2020s and on the right for the 2050s. So we can use these and apply advanced statistics to enrich the data set to generate probability maps. And the advantage of numerical models is that we've got consistent data. We know the historical archive can be susceptible to artificial trends and biases due to changes in the observing methods. Now, these models are physically based, so they take into account climate variability and climate change, and they're able to produce events that do not have a historical precedent. And here's just a snapshot of the level of detail we can get from these decadal models. This is a snapshot of a Cat 3 hurricane in October 2046, making landfall on the Gulf Coast. So that's just to give you an idea of the level of detail. This is model-derived satellite imagery. Now, these data sets are great for digging down into the mechanisms of clustering of hazards. Here's a snapshot of model-derived satellite imagery and low-level winds. And we know tropical cyclones can develop from waves in the atmosphere. Sometimes each wave develops into a tropical cyclone, but during other periods, none of the waves develop into cyclones. And this can lead to clustering and dependency of events. So we can really dig down into the statistics of this and the physical mechanisms. And we can also look at dependency between hazards, for example, cyclones and European windstorms. Now, coming down in scale, that previous model I showed you was run at a grid spacing of 36 kilometers. We're coming down to 4 kilometers now to look at the level of detail. This is an example of a simulation of Hurricane Rita in 2005. On the left is the wind speed colored and the wind barbs. So you can get information on the scale of the damaging winds. And on the right is the model-derived radar reflectivity. So the model can produce information on possible flooding rains. Now, these detailed models are very expensive to run. That Rita simulation took 4 hours on the supercomputer, whereas we need models that can be run hundreds of thousands of times to generate probabilities. But we can use these expensive models, the weather model, to inform the development of a more simple model that's cheaper to run, and you can run it many times. It's just shown conceptually there in the bottom, where the height of the surface is the wind field around a hurricane. And so this simple model can then be applied to synthetic storm tracks. And an example is given on the right here of a synthetic track making landfall over Japan. And so you can generate hundreds of thousands of these to generate statistics. One other use of numerical models is detailed reanalyses of past events. And I'm just showing an example here. This is to understand the nature of the hazard. This is from the USGS multi-hazard demonstration project. So this was designed as an emergency preparedness scenario for the public of a winter storm impacting California. And you should be able to pick out the Sierra Nevada there, and the colors are rainfall, and so the purple is up to 3 meters of rainfall. This is a simulation of an event that hit California in the winter of 1861 to 62, where the whole Sacramento Valley flooded. And so we can use this atmospheric data to then drive flood models and erosion and inundation models, and then look at the societal and economic impacts to would this event happen again in the future. I'd just like to finish going down even further in detail. This is the eye wall of a hurricane. The spatial scale is 37 kilometers square, and this simulation was run at a grid spacing of 62 meters. So this is an unprecedented detailed look of the eye wall of a hurricane, where we're actually directly simulating turbulence. Now, we usually think of hurricanes in terms of the 1 minute mean wind, but it's not the 1 minute mean wind that causes the damage. We often quote the 3-second gust, and here you're looking at the gusts. And the instantaneous maximum wind speed from this simulation of a Cat 5 hurricane was 270 miles an hour, and this is much higher than the 1 minute average wind speed of 155. So we can use information from simulations like this to try and inform the development, again, of simple models to try and include this important timescale structure of the hazard. So just a few finishing remarks. Well, we're on the dawn of a new era in risk assessment, and weather and climate models are a powerful tool. and it's certainly an area that's rapidly developing and a fertile ground for collaboration and progress. Thank you.
Well, thank you to James and to Tom for giving this great introduction to the modelled world. I must say, with some of the runs we've been looking at, we've been as interested in the climate modelling runs of the current state of the climate system as much as that in 20 and 40 years' time, because we sense that historical data isn't perhaps giving us the best understanding of the extreme parameters. And actually, that's my segue into Pete Daly's talk. Thank you, James. Pete's from one of the leading cat modelling companies, and over the last 20 years, those firms have really enabled our industry and indeed our client bases and other stakeholders to become far more resilient to Mother Nature. And traditionally, the cat modelling companies had used historical data to inform those models. But in the last few years, they've been seeking to inform their work with the sort of climate modelling which Tom and James have just shown us. And certainly, there is no one doing more work in this field than applied insurance research. And Pete leads the atmospheric modelling teams at AAR. And delighted, Pete, that you could join us and take us through the journey now from hazard towards risk and loss.
Actually, just looking at the pamphlet that we all received, the Understanding Risk Handbook, which actually on the cover inside reads, "Can we measure risk? And if we can understand it, can we actually manage to it? Can we actually manage the risk?" And that's really the purpose of my talk, is actually to give you a sense of how the cat modeling firms are approaching the problem, at least from AIR's perspective. The approach is the same as our conventional approach for understanding risk today, which is to try to get a sense for what the state-of-the-art technology can tell us about the climate, and then to quantify the risk. Quantify, in this case, the risk from climate change. It's actually quite a challenging endeavor, because you've already heard the challenges that come from simply modeling the climate itself. Projecting the climate comes with additional uncertainties, but then to project those future climates onto a future risk landscape, which includes the exposure and potential changes that may come across society and the economy over time, can really have major additional implications on the uncertainties that come with it. So instead of just kind of throwing our hands up and saying, well, we really don't know what will happen, we try to approach the problem from a sensitivity perspective and saying that the future climate may hold these sort of conditions, and those conditions could lead to these kinds of changes in risk. So just to give you a sense of really what the cat models do today, the real benefit of a cat model is its ability to measure and quantify risk. In the case of a catastrophe model that we're building, for example, for measuring hurricane risk or extratropical cyclone risk and flood risk, it comes in the form of a measurement of property risk to real estate, essentially. Property, but it also can apply to, say, agriculture, which is another form of real property. Workers' compensation, extreme mortality. These are all forms of insured risk that can be independently affected by changes in climate. Of course, exposure is a critical part of the analysis. We need to incorporate a particular portfolio of exposure which may be more or less susceptible to climate depending on the regional density of that exposure and the kinds of perils that will affect it. For example, hurricanes may affect one part of the world but not in another, but say in another part of the world maybe flood risk is the prime component of risk to be considered. And then finally, what's most important from a cat modeling framework is decision analytics. Interpreting the output of a cat model is no different than interpreting the output of a climate model. Unless you understand how the model has been built and you understand the uncertainties that are implicit in its output, you run the risk of over-interpreting the output, or on the other hand, not understanding the output. And in either case, the value is kind of lost there. So the real critical aspect of all of this is not only understanding the output of a model, but understanding the uncertainties that are implicit within it. So given that, the current approach to modeling and simulation in the cat modeling world is to really approach the problem in a holistic way by generally running Monte Carlo simulations, which is a very large number of individual simulations of events that will kind of impose complete coverage on the area that you're interested in understanding that risk. The simulations of real-world systems have come a long way since CAP modeling's inception in the late 1980s. In that time, there's been a great deal of data that's been incorporated to improve the models. This includes claims data, actual claims information that give us a sense of what kinds of damage have been caused by historical events, and then an understanding of the engineering aspects of individual properties and how they may be affected by, say, wind loads, snow loads, and other aspects of potential damage. Now, the future of CAP modeling, and this is where kind of climate comes into play, is to try to couple CAP models with other state-of-the-art models that may be available to us in various forms, but may not have been sort of attached onto a CAP model to measure the potential impacts. And in doing so, what we'll take advantage of is actually to fill the hole of a lot of what we have challenges in just developing a CAP model in the first place, which is a better understanding of the physical ramifications of a changing climate. And to do that, we take advantage of the kind of models you've already seen so far today, climate models, which are generally global simulations at a relatively coarse resolution, coupled with what we call mesoscale models, which are models that have a boundary to their domain. They're smaller in domain, but they're higher in resolution. That allows us to kind of zero in on the physical dynamics of developing systems like hurricanes, for example. We also can take advantage of remotely sensed data. This can be actually hugely beneficial in just providing us a sense of the landscape that we're actually dealing with today. But remotely sensed data can also provide us with information that we can't directly observe on land. And this can be hugely beneficial, for example, in developing a model of hurricane genesis, which generally takes place well offshore, well away from the human observing systems. Now, here's one example of an application of global climate models in a CAP modeling framework. What we're seeing here is a simulation over the globe of a particular area of the domain where we can extract from the global simulation a piece of the puzzle here, one piece of that domain, but also taking a closer look at one particular peril that can influence risk. In this case, it's precipitation, which then goes on to produce flood damage. Now, one nice thing and a huge benefit of a climate model is that the climate model, as you heard James describe earlier, is physically correlated. The inner workings of the model understand the relationship between correlated atmospheric variables. In this case, you're seeing that correlation between precipitation induced by an extratropical cyclone over Europe and the wind speeds that that same extratropical cyclone produces. In the absence of a physical model, that correlation would have to be enforced in an artificial way. With making use of a climate model, we get that correlation naturally. It's enforced within the model itself. And that means that the correlation between these important potential impacts that can lead to damage are kind of enforced within the modeling framework. Now, one huge and important aspect of making use of climate model data is to acknowledge that there are uncertainties associated with this resolution. Generally, global climate models are run at a fairly coarse resolution. We're talking about each grid cell on the order of, say, 50, 100 kilometers, actually in its more high-resolution state. So in order to get a sense of what we need to develop a CAP model is a fine-scale, local-scale depiction of the risk. And in order to do that, what we generally do is take advantage of what you saw earlier, the global climate model simulation of an important peril, in this case precipitation, and then downscale it to the local level. To, for example, simulate flood, we have to understand the individual floodplain at the much more local scale to know what the runoff of that precipitation will lead to and ultimately induce local flooding. Another huge challenge in CAP modeling is understanding storm surge risk. This is the water surge that comes with hurricanes and generally can produce extremely important damage to acknowledge, in some cases exacerbated damage on the level of even the winds from a hurricane. Here you're seeing from Hurricane Ike some observations of surge well inland, very difficult to model if you're simply modeling the barrier of water that's going to come up to the shoreline around Galveston. You then would have to have a very fine-scale river model to understand how the implications of that flood could actually propagate well inland. You actually see some of the largest surge heights on the order of 13 feet well away from the shoreline, where actually lower surge heights were simulated, or were observed and would be simulated by a physical model. So by taking advantage again of climate model output, we can actually downscale by running a finer scale model, a mesoscale model, to simulate the actual evolution of the surge. In this case for a historical event, Hurricane Ike, but we can also do so for simulated events, events that have not yet occurred, but could occur in the future of different intensities and different locations at landfall. And that's really the huge value in a CAT model, is being able to simulate the total spectrum of potential frequencies and intensities.
Just a minute to go.
Sure. So still, even with a model of that sophistication, you're still going to have challenges in reproducing historical observation. You see in this case, some of the gauges offshore are actually very well produced by a model, but some of the gauges that are slightly inland are actually problematic for the model. And this is always going to be the case as the complexity increases and the scale decreases. So just to kind of finish off, give you a sense of some of the projects that we've taken on in the area of climate coupled with CAT models, one of which you'll actually hear a little bit more about later. Matt Huddleston here represented the Met Office on one of the studies that we accomplished last year for the Association of British Insurers. This was a partnership between AIR and the Met Office, in which Met Office really took on the sort of atmospheric climate piece of the project in understanding how future climate regimes may impact the frequency and intensity of flood events in the UK and typhoon events in China. Now, being very different parts of the world, a developed and a developing part of the world, we also looked very closely at socioeconomic effects of the potential future risk. And that's a very important aspect of obviously what we're talking about today here. We've also looked at the impact of sea level rise on storm surge. Here, the idea is that if the sea level rises, then the typical level of storm surge, as you saw with Hurricane Ike, would be that much higher and therefore penetrate that much farther inland. So there's an implication even just on storm surge risk from the simple idea of a rising sea level. And then finally, we looked at the impact of ocean temperatures in the Atlantic Ocean on hurricane risk. So these are all cases where we take a catastrophe model that's already been built to measure the risk today, and we incorporate future climate regimes projected into the future, 30, 50, 100 years, to understand not what we expect to happen in the future, but the sensitivity of future risk to the conditions that could come over time. There's a slight distinction there between a prediction and just the sensitivity of the risk to the climate as it changes. We've also published much of our work, and I'd be glad if you are interested in sharing some of this with you. A lot of it is available on our website, and I can also pass along the material if you're interested. So with that, I'll just leave up the summary, and thank you for your attention.
Peter, thank you. And Pete's almost introduced Matt Huddleston already. Within the European space, the UK Met Office and the Hadley Centre is one of those other major climate modelling centres. There's probably a little more than a handful around the world, and we've got 3 of them here. And the Met Office is also amongst the pioneers of operational climate services. This is the idea of being able to project weather risk beyond the traditional 5-day or 2-week horizon into months, seasons, and almost years ahead. This has huge implications for us in the insurance world, but actually, of course, even more so for those of us who are worried about civil protection. So, Matt, over to you.
Where do we expect the extreme events to happen this year? Where do we expect them to happen next year? Where are those events going to happen on the timescales that we can make decisions to put adaptation in place to respond to those events? So whilst climate change shows the direction of travel, and it's very important to understand where we are going and the implications of our activity, operational and day-to-day decision making demands that we provide information on the timescales of those decisions. We've got to turn around the climate science that's been done over the last 20 years and make it relevant to risk management. So we've made a start. This is an early trial service that we've launched this year, and we're working with Willis and other partners to try and provide some of the climate science that has been described this morning in a way that's relevant to decision makers. And we've got a long road to travel, and it's a very exciting set of things that are coming together, because we're learning a lot as climate scientists about the user need. The best science is done when the question that you're trying to answer is understood well, and that drives better science. So science is not an end in itself, it's about helping users to make decisions. So we have a set of services that are now ongoing and being developed on a range of timescales for the insurance industry, but also in terms of climate risk management in Africa. I'm not going to speak especially about that this morning, but I'm happy to talk offline. Weather forecasting has developed massively over the last 50 years, as Rowan introduced yesterday, and that is a combination of understanding the here and now, the antecedent events, what is the weather and climate doing right now, and then propagating that into the future and understanding those risks. Now, climate forecasting is the same thing, but looking at the next 6 months, next year, next 2 years. So we're combining climate model technology, understanding the boundary conditions of carbon dioxide, of volcanic eruptions, of other implications on land use, with weather forecasting technology when you understand the antecedent events and the initial value problem, what is here and now, and forecasting that future. There's decisions being made on every time scale that are relevant to weather and climate, and there's a few listed here, and understanding the thresholds of users' needs is key. We are not going to remove uncertainty. Uncertainty is good. Uncertainty is honest about our ability to understand the true world. Models are not truth, they are pointers towards the truth. If we use uncertain information, we need to understand the threshold of decision making. At what height does water overtip a barrier? At what threshold do we invest a lot of money to put resources to mitigate flooding? Last year was a very quiet El Niño season as far as hurricanes were concerned. That meant that natural climate variations had a big impact on our world, and those natural variations are the most relevant thing on the timescales of decision making. Most of climate science has done all it can to remove the natural variability from the climate change signal, because it's too short term, it's noise in the system. But in terms of decision making, natural variability in terms of where the floods and droughts are going to be, where the storms are going to be, is the important component that needs to happen. And that is a nascent science, that's just happening, it's very difficult. Climate models are not always that great at representing the natural system. However, El Niño is the biggest component after the seasons of natural variability, and is modelled relatively well, you can say. Now, in terms of mean, in climate change, we're used to talking about mean temperature changes, say a degree of warming that's already happened. In terms of extremes, in terms of disaster management, a small change in the mean means we overtip the thresholds that impact users exponentially, much higher than just a small change in the mean. So while climate science often can only really talk about the mean, we understand well the implications on extremes. And that is true for natural variability as well. That is true for an El Niño, and it's true for other components. Running into European winter, just to give you some examples, last year we did some analysis of these different components. Climate change is a factor. It's a small one at this current time in terms of temperatures. But there's a whole family, a zoo of other beasts you may not have heard of. The quasi-biennial oscillation in the atmosphere, the North Atlantic oscillation, El Niño, volcanic activity. I saw this on this chart last November, and I thought, why have we put volcanoes in there? Little did I know we're going to be running into one early this year. In terms of tropical storms, though, climate models, whilst not very granular at this time, are able to do a very credible job of forecasting near-term tropical storm activity. So we've shown that over the last years, in operational mode, not just hindcasting the past, that these models can give very credible information, for instance showing the very underactive year last year where there's this high wind shear which Tom described. In 2005, if we'd released this forecast, it said that a season was predicted that had not been experienced in recent living memory. That means climate models have the ability to forecast outside the experienced box. They have the chance to tell us the things that we haven't experienced in the past, and that's why they are critical above just historical analysis. Now, going into this year's tropical storm season, we can see a very highly active season is predicted. This also follows from the climate models, and we're working closely with the insurance industry to interpret what that may mean. In terms of Earth system modelling, though, it's important that we do include things like volcanoes, land use change, and that climate models have this potential to amalgamate all these complex signals together. They have the causality within them. In researching volcanoes, I found the Tambora eruption of 1815 caused a global temperature drop of about 0.7 degrees C, which is the same scale of warming as we've had over the last 100 years. Now, the impact on that meant there was snow in New York in June, and the rivers in Philadelphia had ice on them in August. There were riots in Germany and in England for food. What happens if a Tambora goes off tomorrow to our risk management? Who is going to quantify the risk? Climate models offer that potential. It's not going to be easy, but they have that potential. In terms of the next 5 to 10 years, climate models are being used already. It's a noisy scenario. You see the black line, it says 1985 is what's happened. There's lots of ups and downs caused by things like Mount Pinatubo in 1992. And you can see the green then is the forecast from now going forward. It's uncertain because that's honest about the uncertainties in the modelling and the climate system. It could be like that, where warming is experienced very rapidly with an El Nino going on. That might be a reasonable scenario. It could be like that. It could be a volcano that goes off and cools the climate. Either way, there's a very high chance of being warmer over the next few years than the warmest year on record, 1998. As was just explained by Peter, taking climate models and making them decision relevant means working with the industry experts. One aspect of the research we did that showed that natural climate variability could be very costly and is not always taken into account. A small southward shift of the storm track in Europe could mean a massive impact in the kind of losses that we could see from natural events. So in terms of a climate service, it will be a global picture. It will be many institutes working together. Collaboration is key in driving the user need back to the science. Climate variability is key because it's relevant on the timescales on which decisions are made in every region of the world. Weather and climate science is now at the place where it can make useful contributions to decision risk management. And there are tools on weather risk management that are ready to be exploited in terms of adaptation and managing and transferring risk around the world. And the key thing is that in this risk management, it must enable decisions. It must allow people to shake hands around the table and act on the end of it. Thank you.
Thank you very, very much indeed for that. We're now going to move slightly outside of climate modelling, and I'm absolutely delighted that Howard Kunrather could come down from Wharton in Philadelphia. Howard runs one of the major centres of cat risk finance and public policy and decision making in the world. Howard's quite a doyen of this field, and what we're going to be discussing now is how these sorts of climate models are beginning to inform economic decision making and public policy, both here in the US and elsewhere. And there's no one better to discuss this than Howard. So Howard, thank you for coming down all the way from Philadelphia.
Thank you. Yes, it was a long trip. Delighted to be here. Well, I want to really build on the talks that we've just heard by Tom, James, Peter, and Matt, to raise some questions with you in terms of what we can do to address the issue that has been stimulated by a lot of the models that we've just heard. And I think that Matt's last point on the importance of adaptation is going to be a critical part of at least what I want to talk about. How can we reduce these losses in the future? So let me give you a quick overview of what we want to talk about. First point is we are in a new era of catastrophes. The data speaks for themselves. I think we've all observed this, and I want to just point out essentially some of the data that we've been looking at that, and a lot of everyone around the room is aware aware of, I think, but just to highlight the fact that we are in this new era of catastrophes. Then I want to highlight the importance of adaptation measures, and we did a study with the World Bank on just this question with the International Institute of Applied Systems Analysis and one of the other modeling companies, a friendly competitor, Risk Management Solutions, to begin to look at the issues of adaptation and how that played out. Then the question is, what's the potential losses from different scenarios, the impact of climate change, which we can show in the context of the St. Lucia example, and then some summary and challenges. So let me get started with the new era of catastrophe. A few very key points. We have this radical change in the rhythm of catastrophes. Natural disasters have caused more fatalities and damage in recent years than in the past. The challenge, of course, is that the victims complain and they say, we need relief, we need disaster relief. There aren't steps that are taken beforehand, and of course, we do all come to the rescue for a lot of obvious reasons. And so the challenge is, how can we do things beforehand to reduce these potential losses in the future? Here are some data. This is insured losses around the world. And it's very, very interesting, the insurance industry, when they were asked questions back in 1987, the last year in this first panel here, or next to last year, as to how they would predict the losses that they would suffer from severe hurricanes. They came up with a scenario of 2 hurricanes in 1 year with a total of $7 billion worth of damage from the 2 hurricanes. And they apologized for having such a large figure. And as we know, this has been greatly dwarfed by single disasters, with Katrina itself causing $46 billion of just insured losses. Forget about all the other losses that were uninsured, and in the emerging world, most of these losses were not insured. You look at the second panel, you can see what's happened, and then here are some of the data from the last first 8 years. In 2008. We have a major problem today, and the question is, how do we deal with it? And a lot of the first 4 talks have really raised the issue of how do we begin to address the climate change as a part of it. So I think there are 2 factors that I think are important to put on the table. One is the higher degree of urbanization. Without climate change itself, we have more and more structures at value at risk. And if you want to look just within our own country, and this would be true in other parts of the world as well, the population of Florida, 2.8 million in 1950, 6.8 in 1970, 13 million in 1990, 19.3 million in 2010, a 590% increase in terms of people who are living in that area, and most of them are living along the coast. It's a nice place to live until you have a hurricane, and then we all know some of the challenges that we face. So the cost of Hurricane Andrew that occurred in 1992 would have been double to $120 billion had it occurred in 2004 because of this increase in population. The other aspect, of course, which is a theme of certainly of our discussion here today, is weather patterns, and we've heard a lot about that, the changing climate conditions, the variability in hurricanes, and then always the notion that we are in more intensive weather-related events. And so the question, of course, is what's going to happen this year. And we've had our forecast that we're all very aware of as of the last couple of days, that this might be a more intense year, and so we have questions in terms of how we're going to deal with it. So that's the data in the new era of catastrophe. Let's take a look now in terms of how we will deal with adaptation. I don't have to go through this because that already was done very well by Peter and by others and who talked about the fact we've got models, hazard modules, exposure models, vulnerability modules, and then how do we convert these into exceedance probability curves, the likelihood of losses exceeding a certain amount in a financial module. And these are the techniques that we, of course, we're using in the context of our World Bank study. Now, here is an example of what would happen to houses in St. Lucia as we were looking at losses from potential hurricanes with various amounts. And on the x-axis, you see the losses. On the y-axis is what's the likelihood of that happening, which is what an exceedance probability curve is. And all that this shows is essentially different structures and what might have occurred. Now, the question that we were raising was, if you did adaptation, if you were trying to reduce the losses by making these homes safer. One option was roof reinforcement. A second option was opening protection with the windows and the doors as a way of trying to reduce the potential losses. And a third option was the combination of both of these things, roof upgrade and opening protection. And what you can see, and I'm just going to point this out just as an illustration of the kind of analyses that can be done using catastrophe models, using the climate change scenarios as a part of this, is you can begin to see what essentially would happen as you begin to look at benefit cost ratios, one being the critical value. You can see that, the heavy line. Anything above 1 will suggest that this is a useful measure to undertake. The problem that we have, and this is an area that I won't have a chance to talk about in great detail right now, the problem we have is how do we get around short-term time horizons? If you look at any of these measures and you'll ask yourself, is it worth our while to do these things in next year with the benefits from next year, we will be in a position where we might say we wouldn't do them, but over a long period of time, even with discount rates, these things become worthwhile. And so it's a real challenge in terms of how we go forward, and we certainly can talk about that if people are interested. Here's the data from 4 states that we finished as a part of a study at war with the weather in the United States. And I think the only point to highlight here is if you look at hurricanes of different magnitudes, this happens to be a 500-year event, a very severe one, you could have reduced the losses by more than half had you had adaptation measures in place. So that's, I think, the challenge that one faces. Climate change scenarios can be then imposed on this, and this is an example of several different scenarios with the bottom curve being the long-term average without climate change. As you have climate change that is introduced here, these losses are going to get more severe. And that's what we've been talking about in terms of these first 3 talks. There's uncertainty around that, but I think the notion basically is that the losses will be worse. So, to just conclude very quickly here, what do we need? And this is really work that we're involved with the Realist Re-Network and with the London School of Economics and the climate scientists. How do we begin to understand the impact of climate change on the frequency of floods and storms and hurricanes of different intensities? What's the impact of climate change on sea level rise, storm surge, and damage to structures with and without adaptation measures in place? And the cost of adaptation obviously has to be considered. And what we can do, and what we should be able to do, is compare the damages with adaptation and without adaptation. And I think this is where it can be quite revealing. And we've just looked at the results of a couple of the studies that have been referred to earlier, the ABI study as well as a study by Lloyd, I'll just mention in a moment, that if you begin to compare the expected damages to structures without adaptation and no climate change over the next 20 years, D, that's the little letter D, compare that with adaptation measures and climate change, D prime, the question is going to be, when will D prime be less than D? And we already have some data, and it came out of this Lloyd study, and we also have data from the ABI study that Matt and Peter were referring to in terms of what will happen with climate change. And the basic conclusion that came out of the Lloyd study was that your D prime, adaptation with climate change, will have lower losses, significantly lower losses than no adaptation and no climate change. The challenge is, how do we get adaptation measures in place? And that's really, I think, what a lot of this conference is partly about. So, very quickly, in summary, 3 points. New era of catastrophes, growing concentration of value in high-risk areas, more devastating disasters to come. Reality, climate change is likely to increase these losses in the future, and the data speak for themselves. Adaptation measures can reduce these future disaster losses. The challenge, and this is where I think we have to be going in the next few years, how do we provide appropriate incentives, economic, psychological, social incentives, social goals, very important. How do we communicate information and have well-enforced standards so that cost-effective adaptation measures are undertaken? Thanks very much.
We're keeping fabulously to time, and as chairman of this session, or session leader, I really had only one real challenge. I knew I had 5 brilliant speakers. I knew I had a compelling story. But the question is, how on earth do you create a finale? And for that I was able to invite Mariam Golnaghi, who I'm delighted has been able to come for literally the day from Geneva. Mariam, please. I was lucky enough to be in Geneva about last September at a meeting called World Climate 3. I don't quite know how I was there, but I was. And the first one of these meetings took place 20 years ago. I think it set up the IPCC. The second one set up the Kyoto Protocol. And this one was all about setting up climate services. About 3 months later, I was sitting around the table with Claudio and Philip and a few others at the GEM Governing Board, Earthquakes, and this lady was around the table. And we had a few interesting discussions, and I suddenly realised it was Mariam, who heads up the Disaster Risk Reduction Programme at the WMO, who actually pretty much drove that whole meeting, which had about 3,000 people there. I said, aha. Anyway, delighted, Mariam, you can be here. You'll have heard some of the stories that Matt was describing about climate services. What Mariam is going to do is take that and illustrate the big picture.
Thank you very much. It's indeed a pleasure to be here, and I by no means can compete with the other speakers. I'm sort of en route from one trip to another, so I would like to excuse my slides, but I will talk more than showing slides. I see a lot of familiar faces because we started on this venture in late 1990s in the US to really try to bring climate modeling to risk management, and it is, for me, the most exciting time in history where we are seeing the best minds around the world are really looking at the issue of climate risk and enabling development of information that can facilitate decision making. What I'm going to talk to you today is a vision for the next 10 years. Imagine over the next 10 years where you have a world where climate information that's produced by some of the best centers today related to really predicting the probabilities of extreme events will become operationally available in every country so that various decision makers at governments, from private sector and various sectors can take that information and do good things with it. Okay? What we have heard today is still, this is an area in research and development, and it still sits within the research community. What I want to talk to you about what is happening today to make this type of information available operationally to everybody. So just quick statistics. We stay up at night a lot because something about 70% of disasters, 75% of economic losses and loss of life are caused by hydrometeorological hazards, something that World Meteorological Organization, working with the scientific community, with meteorological services, with hydrological services, has the mandate to ensure that these are monitored, detected, forecasted and provided to the decision makers. So looking at some of these statistics around the world, we see that from one region to another, what I'm showing in blue are hydrometeorological hazards and their impacts are prominent. So we have something very serious to worry about. We need to manage these risks. And in context of what we've heard from IPCC fourth assessment and a lot of the studies that are coming out, this is something that is going to require significant risk management. What we see is every day, with occurrence of every disaster, particularly in developing and least developed countries, socioeconomic development is at risk. Countries that are recurrently experiencing this kind of disasters, their socioeconomic development is being set back. So we need to really mobilize and do something about it. Okay, let's go back to the history of weather and climate forecasting. You've heard today the state of the art, okay? But all the work that you see today, you know, with tropical cyclone warnings being issued and all of that, is really the result of coordinated research among scientific community within academia, centers of excellence and operational meteorological and hydrological services to understand the dynamics of the phenomena, to develop the type of tools and technologies that we discussed today to be able to predict these things going forward. So any advanced information we can get to better manage the risk is important. And what essentially has happened over the last several decades is significant advancement in understanding of individual phenomena from tornadoes to tropical cyclones, so on, to development of those kind of forecasting tools that gives you lead time from the next hour to the next 72 hours, which has led to development of early warning systems. But very importantly, can we get advanced information with lead times that are relevant to decision making, medium term and long term? And that is essentially the work that scientific community put together with the force and coordination of World Meteorological Organization, starting in the 1970s. And through the World Climate Research Program, a lot of scientists have come together to develop and share and their experiences. That information, what is happening through World Climate Research Program, where all of our speakers are essentially part of that community, what is happening is that information is being consolidated into the IPCC reports that are pushing the international policy negotiations. But what I am here today is, can there be a day where this kind of tools and technologies can translate into operational information for decision making? That everybody can go to a climate center in their country and get this information. Okay, so let me share with you a coordination model that has facilitated availability of tropical cyclone forecasts and warnings around the world. Essentially, when you look at the world, our world is completely coordinated from a meteorological perspective, which means that every day of every year, national meteorological services that have capacity, I want to make a disclaimer, are monitoring and observing various conditions together with space agencies and other technical agencies. That's what I'm showing on the panel on your left-hand side. That information is being exchanged across all the countries through a telecommunication system that is not open to public. It's a telecommunication system that links all the countries of the world through their national Met services. Then through that, this information goes to 40 regional specialized centers that are operated by national Met services. For example, in our country, National Hurricane Center of the United States is an accredited WMO regional center responsible for issuing forecasts and bulletins of tropical cyclones to all the countries in Central America and the Caribbean, whereby then those countries take that information and translate it into a warning. So this coordinated operational work is facilitating very important decision making. We are working to take this model and use it over the next several years to make sure that climate information from seasonal to interannual to decadal and longer term becomes available operationally through national and regional centers for everybody's decision making. 3 minutes, thank you. So let's go and see how is that going to be done. As Rowan mentioned, this September, past September, over 100 heads of states and 3,000 scientists came together at WMO to discuss the challenges with respect to development of operational climate services so that everyone can get access to this information. And essentially, a framework, a coordinated framework for provision of global services at national, regional, and global level has emerged. And essentially, the component of this framework is to make sure that, as I said, climate services can become available through a group of centers, global, regional, and national, to all the stakeholders. This information needs to be driven by the user's needs. So what we saw today was critical. The type of partnership that has started under Willis Research Network between the risk modeling, the Met services, and the climate scientific community is where we want to go, because that is going to be the type of information that we need. We are mobilizing the scientific community to attend to this problem in a more coordinated way. So in other words, the research and development of climate technologies from seasonal to interannual to decadal and longer term needs more coordinated peer review attention from the scientific community. And this is what this framework will achieve. And then finally, establishment of those global, regional, and national centers to ensure that technology will trickle from the leading centers down to national centers, of which most vulnerable are the developing and least developed countries. So how can we enable these countries to be able to produce the kind of information they need for their most vulnerable sectors? So let me just show you one slide so that you can see. This is where we stand today. There are 11 leading climate centers, of which you were exposed to 3 of them this morning, that are essentially at the forefront of climate forecasting and modeling, and I'm very pleased to see that they are moving towards risk modeling, not just hazard modeling. Now, what we hope to do as the network of WMO and partners through the global framework is to ensure that technologies that are developing through these centers will trickle down to a series of regional climate centers which we are establishing, and then that will become the mechanism to facilitate these technologies nationally, like what I have shown you has happened in the weather domain. But we have a challenge. Let me show you some national results. In 2006, I conducted a global survey of technical capacities of countries with respect to development and dissemination of information from weather to climate timescales to address extreme event risk management. Now, this is not a complete picture. This is 74% of the countries around the world. Since then, I have another 20 countries added to this analysis. And the picture is grim. What it is as we develop these technologies, operationalization and provision of information at the national level needs significant capacity development in the countries, particularly developing and least developed countries. What you see is in 70% of the countries, even the issue of risks of climate and extreme event is not a priority at the government. So when you look at their legislation and national planning, you see that they're still in post-disaster response mode. So those kind of changes and revisions need to take place. Secondly, 65% of the national Met services of the world do not have the basic core observation and forecasting capacities to be able to support these type of technologies operationally for decision making. 80% of the national Met services of the world need some kind of a technical and management training to be able to provide from historical databases all the way to forward-looking forecasting and capacities. And then when you look at the partnerships at the national level, you see that the ministries and various entities that need to be working in a cross-cutting way are still working in silos. And that kind of a partnership that needs to be developed to be able to ensure that information flows to risk information and ultimately action cannot be materialized so easily because these kind of partnerships across sectors do not exist. So we have a big challenge at hand, but I think the world is uniting to address these issues from technology to capacity development nationally. And what I'd like to share with you, which I'm very proud of, is that in cooperation with the development agencies, funding agencies, and many other partners, we've started systematically addressing capacity development of countries in a number of regions, starting from data rescue, standardization of data, influencing national planning, all the way to transfer of technology. And with that, I will stop. Thank you very much.
Mariam, thank you very much. If I can ask Mariam, you to stay at the front. If I can ask the other panelists to please come to the front. While I'm doing that, I was struck with your graphic of the WMO sort of system around the world, because actually the insurance industry is another integrated system around the world. Insurers are reinsured and operates in about 190 countries. And certainly we're keen with a few other major industry partners to see how our industry can become a major mechanism to help distribute these services into the countries through the industry. So we'll see what we can do there. Right. very keen for some questions. I haven't had any written questions brought to me by the man in the nice orange shirt. Very keen actually to get some questions. The talks have focused, perhaps emphasised perhaps some of the risks in the developed world, North America, Europe and elsewhere. Very keen to get some questions perhaps from those in developing regions, perhaps with agricultural concerns or elsewhere. So if you have any questions, please get them start them now, otherwise I'll be forced to come up with some of mine. Tricia, name and affiliation please.
Excellent question. I would say you can look at about 12% of countries. I can give you a... Oh, good. Okay, 12% of countries essentially, I would say, are in the red zone. You know, they really we need to work with them on their national policies and then technical capacities from building their observing networks and so on. These 12% primarily lie in Africa, certain parts of Asia, Pacific, Haiti, which is essentially we are losing a lot of sleep over right now. So those are the type of countries. Some countries in Southeast Europe, maybe a couple of countries. So they're scattered, but primarily Africa, Pacific, and some portions of Asia. 42% of countries that we have responses for fall in the orange zone. In other words, they have a little bit of everything, but it's not coming together. You know, they do have observing networks, but they're failing or they're not fully operational or so on. Those countries primarily fit into Central America, South America, some portions of Europe, a big portion of Asia. Then there are countries that I would say in some issues fall in the green zone, but others in orange, where they have good legislation and planning, good infrastructure, but they just need know-how. China is a great example of that. You know, you will see that there is good infrastructure and legislation, but they just need access to the latest technologies. Poland, Czech Republic, so, you know, I mean, I can go on and on. And then there are those that, you know, they have the capacities, the developed countries that are actually helping us in building those capacities, US, Canada, France, and so on. But if you're interested, I can give you more details. Thank you.
Okay. Next question, please. If you can kindly use the microphone, particularly for the benefit of those listeners and viewers around the world, who I will encourage, if you can hear me, to tweet your question now. But in the meantime, name and affiliation, please.
Sure. Pablo Suarez from the Red Cross Red Crescent Climate Center. Thank you to all. I was particularly excited with Matt and Mariam saying that we need user demand, not only to provide services, but also it leads to better science, more useful science. I'm a risk modeler turned humanitarian worker. It's not easy to get users to understand what it is that the experts could provide. So what I'm concerned about is how can we nurture a dialogue process where we don't impose this technical, over-brainy presence that intimidates people who could work with us and are eager to do so, but instantly walk away if they feel that they're perceived as an inferior partner at the table.
I'll give at least one part of an answer, and I'm sure there are many, many different ways. I think it's a very interesting question, Pablo, that you're raising. I think that the real challenge, particularly in the developing world, which I know you have been and others are working in, and people here are concerned about, I think it's extremely important to try to give people not only an understanding of what needs to be done, but short-term returns, short-term ways so that they can benefit in some fashion and understand. And I think there are economic incentives that can be provided. There can be communication, but that's only one part of the story. At the end of the day, with poverty being an important dimension, one has to sort of try to show that if certain actions are taken, there will be enough benefits in the short run for them to deal with it. And a lot of the microinsurance work and a lot of the other things that are being done in many of these countries would be one way to get started. So that's, I
couldn't agree more that, you know, if we go in with a full blown solution of technologies, we've lost the battle. So one of the things we are doing at WMO and with the development partners, we are really trying to assess, first of all, who is the user? You have to identify who is your user, segment them, understand who you're dealing with. Okay, so for example, I deal with governments and there's, the sectors, agriculture and so on. So you need to understand receptivity of that government to these issues. And there is a lot of sort of desktop work that you can do. But then what we've started is, as part of those programs that I showed, doing national policy dialogues, bringing everybody around the table, after having done a detailed assessment of where they stand, and start that dialogue and see where the receptiveness is. For example, when you look at Caribbean, everybody wants to do early warnings. Everyone. You can penetrate into the countries by addressing the next season. There will be tropical cyclones. Whereas when you go to Southeast Europe, and we have one of the leading people from Macedonia, Dr. Pande Lazarevsky, in the audience, you see that drivers are economic drivers. You need to work with the sectors. So that's it. You need to really do homework, and as Howard said, step by step, show some benefits, and then advance it that way. Any other comments?
Thank you. Just a comment on Africa. The Millennium Commission on Climate Change highlighted that the Regional Climate Outlook Forum in Africa, which has for a long time been taking short-range climate forecasts with local native knowledge and the local forecasters and institutes like the International Research Institute of Columbia coming together to help decision making. So it's a long process in getting people familiar with what can be done and integrating it in decision making. And what we've noticed, for instance, in Ghana, we provide a forecast for the Asakumba Dam for the height of Lake Volta. It provides half the electricity for Ghana, incredibly important. Now, what happens if you get a forecast that says it's going to be completely different from their experience? Can the people actually change the taps on the dam to reduce the flow of water? They're not allowed. There's a lot of regulation, even if they understand it, that prevents action. So as Mariam highlighted, there's in every level in terms of adaptation, it's a detailed and messy business in a sense. For every country and every sector, it's different issues.
Thank you. Any further questions? Yes, gentleman at the back with the blue shirt. Name and affiliation, please.
My name is Joshua Sperling. I'm at the Center for Sustainable Urban Infrastructure at the University of Colorado, Denver. My work is mostly on climate change adaptation. And I think the information that this community can provide is very useful for decision making, but it's lacking, I think, two things. I think it's the information, the climate risks as it relates to actions, proposed actions. I think Howard was the first to actually get at that. 150 billion could be saved. I don't know if that's actually true in terms of putting roof insulation on or the two things you mentioned, but I think we need to figure that out, what the 100 billion in adaptation actually means each year, as Ban Ki-moon suggested of the UN, from now to 2050. So I'm working a lot with local governments, and I think that's an area that I think was missing in this conversation. You're talking national, global, and even regional. I don't see the international talks going so far in terms of the climate change discussions, in terms of mitigation. I think a lot can happen at the local level, and so building capacity of urban government specifically, that's where a lot of the infrastructure is, specific actions and how that relates to climate risks. Thank you.
Any questions? Any answers? I do want to bring in Kathy at IBM, who's dealing with smarter cities, and I know you're here, so I'm going to ask you to respond to that as well in a second.
Just one very short comment on your point. I think that first of all, in the case of Florida, where we did show those data, they were very different measures than you would necessarily have with St. Lucia. So I think that the 2 points that I would make is every measure has to be looked at very systematically, and there'll be some measures that are not cost effective, and there'll be others that may be. You also want to take into account the loss of lives, because we did a study on Istanbul, for example, on the earthquake, and you could see a measure that actually didn't look like it would be cost effective on the basis of just the property itself, could be extremely cost effective if you looked at the number of people whose lives would have been saved within that property that would have been avoided. So you have to be very, very broad in sort of dealing with it, and then you have to provide enough short-run incentives like long-term loans for adaptation or mitigation, rather than thinking about people being able to deal this up front, and that comes back to our discussion on the developing countries.
Kathy, can I just bring you in briefly, because I know you've been working with a major sort of network of cities around the world. You'll need a microphone if you can wave. Just very briefly give a highlight of how urban municipal governments are confronting this.
Thank you very much, Rowan. I think the two things that I just wanted to highlight that I've gathered out of today, which match onto the work that's been done elsewhere in academia with cities, is actually looking at the end users. And one of the things I would say is that is citizen-centric in any country. And the context of getting down to what does it mean to the local people and the local economies, you know, within a city, say in India. Actually, there are some common denominators, and simple things like food, water, and electricity, I would say, are pretty fundamental to any city in the world today. And one of the things, as you say, bringing the modelling back to the human level, I think is one of the messages that I've taken away from most of the city work. And there is a World Bank initiative looking at cities, a cities indicator, across the world, which 103 cities have already subscribed to, which will go into an open platform later this year. And I think that is a very interesting piece of work going on in parallel that we can maybe leverage in due course. So the cities side, I think we need to look from the citizen out, and then adaptation will happen because it's contextual to each city.
Okay. Kathy, thank you. Time for one more question. I think the gentleman, your gentleman with the pink shirt had his hand up just fractionally before the gentleman in the blue shirt. So we'll go to the pink shirt first. Over there. There we go. Thank you.
We've also had a question come in from online.
In that case, that trumps everything, because the glamour of having an online question is wonderful. I can't see it on the screen, but you can read it.
I apologize to the gentleman in the pink and blue shirt.
We can wave to the person out there in cyberspace. Right.
So our remote viewer, Getman, asks over Twitter, what of Pacific and Indian cyclone models? Increasing?
Well, for that we must hand over to one of the climate modelers. Who wants to put their hand up first? Tom Knutson.
Well, that's a really important point. My talk focused on the Atlantic Basin because we had this regional model we needed to use to get the resolution high enough. But this increased vertical wind shear that's projected for the Atlantic Basin is not really being projected in many other basins like the Indian Ocean Basin. So we shouldn't look at that as some type of panacea that's going to help things out around the world, if you will. So we are looking very carefully, and in our project we are expanding into other basins with this same type of framework to try to address this question. I think the short answer is that we're seeing some indication of increases in hurricane intensities when we look around the world. But if one looks at individual basins, our confidence in what will happen to storm numbers in any individual basin is low. Overall, again, we're seeing some indication of a global decrease of tropical storm counts, but again, this increasing intensity seems to be present globally, although there may be some modulation of it from basin to basin. So that's where we stand at this point. But also the data sets going back in time are in much poorer shape in some of the other basins than in the Atlantic. And we need to do a lot more data rescue work, if we can, to try to get what information we can out of these data sets, and looking at the past to help inform the future.
Thank you, Tom. I think Pete's also got a perspective he wants to
Yeah, just...
What's the name of our online guest?
Yetman.
What's to share with Yetman?
Well, yeah, man. Actually, I just wanted to make a quick point, actually, on this topic of Indian risk, but also back on some of the previous questions. I think one of probably the hugest challenges in communicating climate risk to especially the developing world that's not immediately accessible to the latest technology is actually the communication question. How do you actually communicate the potential impacts? And back to the question about, okay, can you save $150 billion in the future by adaptation and mitigation measures? When it really comes down to funding these kinds of measures and you go to policymakers and try to establish changes in policy, it's really going to come down to establishing not just the expected change from climate, but the uncertainty associated with it. And how do you communicate that uncertainty when it may be very, very wide, all the way from actually mitigation resulting in actually no change, and the cost, of course, needs to be accounted for, or potential savings? To me, it seems, and this is where, from a CAP modeling perspective, we constantly have to communicate to the layperson what is the meaning of risk and what's the meaning of the uncertainty. When it comes to climate change, that uncertainty is only that much larger because of the uncertainties associated with the hazard, not necessarily just the costs. So I just wanted to make the point that I think a study could be done solely on how do you communicate climate risk in and of itself, not only to developing and undeveloped parts of the world, but also there's a cultural interpretation of uncertainty which may vary across the world. So I think this is where maybe Miriam's work could really come in handy, but I think overall communication of uncertainty is a huge part of what we're trying to accomplish here.
Okay. Peter, thank you very much indeed. We started fractionally late, and we've gone a little bit over time, and I am conscious of our need to maintain discipline. So I am going to beg the forgiveness, please, of the man in the pink shirt and the gentleman in the blue shirt and all other shirts and blouses in the room, and try and draw this fabulous session to an elegant conclusion. But on behalf of all of us, I'd like to thank hugely our 6 panelists for a fabulous talks and attending. I'd like to thank you all for choosing this session and making it such a stimulating discussion, and those viewers and questioners out there in the rest of the world. So thank you all, and I'm sure we will all meet again someplace, sometime soon.